Okay, here we have a combination table. It's a common question, this one, all about what happens to the frequency and the wavelength of monochromatic light when it travels from glass to air. So have a look, and then when you're ready, watch the explanation. Okay, so as I've said, it's a really commonly used question structure, and one that particularly relies on a little bit of sort of factual information. There's not a lot of conceptual stuff here initially. The main point about this question is that to remember what happens when waves undergo refraction is that there's one thing which always stays the same, and that is the frequency. Okay, like I said, there's not a lot of sort of explaining here. There's more just a fact, if you like, that frequency always stays the same. This is kind of to do with what happens at the boundary. If the frequency changes, basically, the wave becomes split up and disconnected, and therefore it no longer forms a wave. So there has to be a continuity between the two phases. You could imagine what would happen if you had a rope and one part started oscillating with a different frequency than the other, it would break. Okay, so the frequency is always staying the same, and this is something that I find students have a lot of trouble kind of really understanding, but it is a key part of these questions. Okay, this allows us, if we accept that, to get rid of a couple of options, which is the frequency will not increase and will not decrease. So we have a choice there. Okay, to determine what really is happening with the wavelength, let's use a couple of equations. Firstly, we've got n equals c over v, and that's our refractive index equation. Now, why are we looking at this? Well, we're going from glass to air. Okay, we're from high to a low refractive index. So what that means is that as n is equal to c over v, that means our speed is increasing. Okay, we're going to go from a wave which is going slowly in glass to a wave which is going quickly in air. Now, why is that important? Well, we should also know that regardless of the wave type, we've got the equation v equal f lambda. This is the wave equation, so called because it applies to all waves. And therefore, if you can see that if v is going up, lambda is also going up, which means that b is the answer here. Now, I would have said that you could get to most of this just by remembering one small fact here, which is that the frequency always remains constant. Okay, the likelihood of the wavelength not changing and the frequency not changing as well is very low, and so therefore you've got a good kind of likelihood of getting the answer. But as you can see, this is why the wavelength is increasing here.